Okay, this video is on solving log equations, and this is again used when we have variables in the exponent position and we can't solve them in that. We have to isolate the x. So there's two basic formats that we're going to go through in this video. So again, the two objectives here are, can we convert from exponential form to log form in order to isolate the variable, and can we solve for variables in the exponent position? So there's two things to look at here. Alright, so take a look at this example right here. So notice we have the variables in the exponent position. Okay, so we have a variable here and a variable here. So to get it by itself, we can't really look at it here. And the thing is, we can't really combine anything because both the 9 and the 27 are different bases. So what I like to do is, if I can convert and get a common base, then we're going to have the same thing. So let's take a look here. If we have this a small example to decide, if x is equal to x, and that be true if we have x to the y power, and then this has to be x to the y power. So if the bases are the same and they're equivalent to each other, then that means the exponents have to be the same. So this only works if the two bases are the same. Okay, so let's take a look over here. I'm going to convert 9 to 9 squared, and again this is to the 2x power, and 27 is 3 cubed. And again, that's to the x minus 1 power. And what we saw before is we want to then do power to a power and multiply those exponents. This is 3 to the 4x is equal to 3 to the 3x minus 3. All I'll do is distribute that 3 times x minus 1. So now that the bases are the same and the equation is equal to each other, then we can assume that the exponents are equal to each other. So off to the side, I can just set up the separate equation and say, alright, there we go. So we simply move the x over, and x is equal to negative 3. Okay. And again, you can plug it back in to check and go from there. But again, if we get the bases the same, then the exponents must be the same. Let's take a look at an example, and this one's a little different because notice we have fractions here. So again, when I see 1/2 and 4, those are both based on base 2. So 4 is 2 squared raised to the x power, and 1/2 is really 2 to the negative 1 power, right? That's 2 in the denominator. So again, this one I like to put everything in one line. Don't worry with not the numerator and denominator. Put everything in one line and use positive and negative exponents. So this is x minus 3 here. So we have 2 to the 2x is equal to 2 to the negative x plus 3. I just distributed that negative 1. Again, I'm just multiplying exponents here and here. Okay. So the bases are the same. So off to the side, put the exponents equal to each other. Okay, so we have 3x is equal to 3, and x is equal to 1. Okay, so again, pretty straightforward. Again, this works if you can get the bases to be the exact same. Okay, here's one more example. So again, I see 81 and 1/3. What am I thinking in the back of my head? 3 to some sort of power. Okay, and a circle meaning what goes there. So this is 3 to the 4th power, and this is 3 to the negative 1 power. And again, then I'm going to raise it to the 3 minus x. I'm going to raise it to the 5x minus 6. So we have 12 minus 4x for the exponents there. And here we have negative 5x plus 6. So all I'm doing is looking at the exponents now because I know the bases are the same. So now I'm going to move x over here, and we got negative 6. Okay, so the simplifying basic algebra there. Move the 5x over, make it positive, and move the 12 over and make it negative. Okay. Now, that doesn't always work because here we notice we have a variable here and 4 and 11 nowhere near the bases. So the exponent is stuck in the exponent position. The variable is in the exponent position. So how do we get it by itself? Because we have this base in the way. So we have to convert it to log form. So now we have log base 4 of 11 is equal to x. Okay, and now we have the x by itself on one side of the equation. So now we can use change of base in your calculator, and I'm going to do log base 10 of 11 over log base 10 of 4. And again, let's put that in the calculator real quick and see what we get. So we're going to do log of 11 divided by log of 4. And we get 1.73. Okay. All right, let's take a look at our examples. Again, really simply here. Again, the variables in exponent position, so I want to convert to logs to get it out. Logs basically get rid of the bases. So we have log base 2 of 5 is equal to x. And again, we just used, again, change the base formula, and we get the answer from there. Okay, so again, we changed forms here to get the variable out of the exponent. Whereas the other examples, what we see here, it's okay to leave it in an exponent position if we get the bases the same. So you have to get something the same or something to eliminate. That's the key. All right, so let's take a look at this one last example here. Now right here we have a couple more things in there. So again, I'm going to do log base 7 of 15 is equal to 9x. And then the last thing we do is we just say, hey, let's get x by itself and divide by 9. So this is a value in the calculator. That's log 15 divided by log 7. Get that value, and then divide by 9, and then you're there. Okay, so if I'm going to put it in my calculator, how I would type it in would look something like this. I'm going to do log of 15 divided by log of 7. So that's the top. And then I'm going to divide it by 9. And there's my value. And what was it again? It was 0.15. Okay, and that's pretty much it. And like I said, we'll look at more complicated examples, but I just want to show those very basic examples on how to isolate a variable in the exponent position, okay, and solve for it.